Good evening, everyone, and thank you for joining us for tonight's program. I am David Cole. I think I know many of you. I'm president and CEO of the Science History Institute, and it is my great pleasure to welcome you to the 34th annual Ullyot Public Affairs Lecture featuring Dr. Omar Yaghi. Endowed by distinguished chemist Dr. Glenn Ullyot, this annual award and lecture is both a recognition and an illustration of how the chemical and life sciences contribute to the public welfare. Glenn Ullyot said that, quote, "Chemistry and biology are basic sciences, key to understanding the world around us. It is the aim of this award and the lecture program that each Ullyot lecturer will increasingly stimulate more people to appreciate the positive impact that these sciences and the researchers who pursue them have on our daily lives," end quote. I believe that Glenn Ullyot would be pleased with the history and impact of this award and lecture program as it continues to bring to public attention people of great scientific accomplishment who have changed and benefited the world. The list of past Ullyot Award winners and lecturers is quite distinguished and includes figures such as Robert Langer, Philip Sharp, Jennifer Doudna, Roald Hoffman, Francis Arnold, and most recently, Carolyn Bertozzi. It is our pleasure this evening to add Dr. Omar M. Yaghi to this august roster. This evening's Ullyot Public Affairs Lecture would not be possible without the generous support of the Institute's sponsors and partners, including the Department of Chemistry at the University of Pennsylvania, the Department of Chemistry and Biochemistry at the University of the Sciences, and the Delaware section and the Philadelphia section of the American Chemical Society. Thank you all. This evening, we and our co-presenting partners and sponsors are very happy to welcome Dr. Omar Yaghi to Philadelphia. And now let me tell you a bit about our distinguished honoree and speaker. Dr. Omar M. Yaghi received his PhD in chemistry from the University of Illinois at Urbana-Champaign and was a National Science Foundation postdoctoral fellow at Harvard University. He is currently the Tretter Chair Professor of Chemistry at the University of California at Berkeley and an affiliate scientist at Lawrence Berkeley National Laboratory. He is also the founding director of the Berkeley Global Science Institute, whose mission is to build centers of research in developing countries and to provide opportunities for young scholars to discover and to learn. Dr. Yaghi is also the co-director of the Kavli Energy Nanosciences Institute, focusing on the basic science of energy transformation on the molecular level, and of the California Research Alliance by BASF. His work encompasses the synthesis, structure, and properties of inorganic and organic compounds and the design and construction of new crystalline materials. He is widely known for pioneering several extensive classes of new materials: metal organic frameworks, or MOFs, covalent organic frameworks, or COFs, and zeolitic imidazolate frameworks, or ZIFs. Keep those in mind: MOFs, COFs, and ZIFs. These materials have the highest surface areas known to date, making them useful for hydrogen and methane storage, carbon capture and conversion, water harvesting from desert air, and catalysis, to name just a few uses. The building block approach that Dr. Yaghi has developed has led to exponential growth in the creation of new materials. He has termed this field reticular chemistry, and he defines it as, quote, "stitching molecular building blocks into extended structures by strong bonds," end quote. His work on MOFs, COFs, and ZIFs has led to over 300 published articles, which have received more than 227,000 citations. Indeed, he has been ranked as the second most impactful chemist worldwide. Dr. Yaghi is an elected member of the U.S. National Academy of Sciences, the American Academy of Arts and Sciences, and the German National Academy of Sciences. He has also been honored with many awards. I will only give you a very partial list, which includes the Sacconi Medal of the Italian Chemical Society, the American Chemical Society Award in the Chemistry of Materials, the Royal Society of Chemistry Centenary Prize, the Albert Einstein World Award of Science, the Wolf Prize in Chemistry, and most recently, the Wilhelm Exner Medal. That's quite a list. And so, we are privileged to have in our midst this evening a path-breaking scientist, an esteemed teacher and mentor, and an engaged leader whose research accomplishments, as we shall hear, I think, have made profound public impacts and hold great promise for improving our lives. So it is therefore my great honor to present our 2024 Ullyot Public Affairs Lecturer, Dr. Omar Yaghi.
Thank you, David, for the generous introduction, and thank you all for the warm welcome here. It's really an honor and a distinct honor and pleasure to receive this prestigious lectureship and award. I want to share with you some of our work. What I want to begin with is something that touches all our lives, and it deals with carbon capture. Here is a plot, or here is a satellite map of how much CO2 has been accumulating in the air just since January of 2015. You see here, this bar will be moving from 392 ppm of CO2 all the way up here to the yellow. The more yellow, the more CO2 is being emitted in the air. These are NASA images, and you can see we're already at 400 ppm, okay? In December 2017, already July 2018, now at 409 ppm, 412 ppm, 414 ppm. We are emitting about 40 gigatons, that's 10 to the 9, gigatons of CO2 every year into the atmosphere. There's about 1,100 gigatons of CO2 already in the atmosphere that have been emitted since the Industrial Revolution. This is the effect of that CO2 emission. Almost every year for the last, every year for the last 3 years have been record heat years in the US and in other parts of the world. And we all know about this heat dome that descended on the central US back in 2023. These are becoming more and more common occurrences. Our weather events are becoming more and more intense. And our distribution of water, as I will discuss shortly, have also been affected by the climate change, in that we get a lot of rain, just like in Spain, for example, recently. They got all the rain that they would get in a year in 1 week, okay? And that's not very helpful. The result also has to do with more intense weather pattern, more intense activities, more intense things that we have to deal with, such as wildfires, such as this Woolsey fire, which burned some of the most beautiful places in the world back in 2018. That year, over 2 million acres of land have been burned in California alone. So that's the effect of CO2, but it also affects water, and that has already been a problem for a long time. So water is another issue that I will talk about today that affects all our lives. This is the global stress, and you see here the projections from 2020 to 2040. And you see that significant part of the US is water stressed and will become even worse than that. In fact, places such as London and Belgium that you and I think are well-watered regions will be water stressed. In fact, almost 1/4 of the world will be experiencing a water crisis, not just a stress, but a crisis, meaning that people will not have enough water to sustain themselves. So by the year 2040, we have a progression of a worsening situation when it comes to water. We're using too much of the underground water. That's why you see in the Midwest, in parts of the Midwest that is highly watered, you see that it's going to be water stressed because we're using too much of the underground water and it's not getting replenished as fast to make it useful for us in the short term. This is the Hoover Dam back in 1983. You see the level here. This is the largest dam in North America, and it supplies 16 million people with water. This is in 2003. You see it, okay, being depleted. 2022. Okay. This is just near Las Vegas. If you're ever in that region, you should visit because it really makes a lasting impression on you. So when this water is gone, where are these 16 million people going to get their water? So that's the end of the bad news. Okay, the rest is going to be good news. Okay, because I know most of you are probably chemists. We know what's responsible for these problems, and we know what we need to do, what molecules we need to address to deal with these problems. And one, of course, is hydrogen, one of the smallest molecules in chemistry. Hydrogen, we need to be able to store hydrogen for automobile fueling, for using it as a fuel, because it burns cleanly and only produces water as a byproduct. We need to think more about methane. We need to think about methane as a fuel because it's 50% cleaner than petroleum. So if we turn all our cars today, all our fueling of power plants to natural gas, which we have plenty of all over the world, we could cut the emissions by 50% in a very short period of time. CO2 we need to take out of the air. And no matter what we do in terms of slowing down burning of fossil fuels, we still need to take that carbon dioxide out of the air because it is the stuff that is causing the climate problem. And I will show you how we can take water out of the air to make drinking water and create a new source of water for people on our planet. Well, we know the cause. So now chemists go to the periodic table to solve the problem, right? Because they've been there before. Chemists know how to navigate the periodic table better than anyone else. And we've been working with the periodic table to make great examples of impact on our society, such as pharmaceuticals. Think about the impact that pharmaceuticals have had on the world quality of life, people all over the world, as well as lifespan, lengthening lifespan. Well, the question that we wanted to answer back when I became an independent professor in the early 1990s was, what happens when you take molecules and you stitch them together through strong bonds? What do you make? Okay, that question was potentially asked before, but people shied away because when you start building structures like Legos, the stuff you make is very ill-defined and not so crystalline. You make junk, basically, okay? Stuff that you hardly can characterize. So what we wanted to do, we wanted to stitch them together just like you would do Legos to build different structures, but at the same time, make crystalline materials, meaning materials that have well-defined structure and therefore can have homogeneous properties when you deploy it. So that's the question we asked. So we started with a very ambitious question and we solved it. And when we solved it, 30 years later, we call it reticular chemistry, the chemistry of linking molecular building blocks like Legos, basically, by strong bonds to make crystalline extended structures. We want strong bonds because we want to make materials that are robust, that are going to stay in that power plant not just for days and 1 year, but for a long time, for years, as you'll see shortly. The strong bonds is what gives it the durability that you need for the material to function over and over again for many, many years. Crystallinity is very important because you want your material to be well defined on the atomic level, but also you want the material to behave in the same way every time you carry out the function of that material. The result of reticular chemistry has been metal organic frameworks, MOFs. You see an illustration of one of the first MOFs here. These are metal containing units, metal oxide units linked by organics. And the yellow ball is there to indicate the space within which one can store gases like hydrogen, methane, CO2, and water. So back in 1995, we showed that in fact, these things can be crystallized, even though everybody said they couldn't be. And so we developed methods of crystallizing them that are used until today. In 1998, we showed that in fact, they can remain open in the absence of anything in the yellow ball. So they are architecturally robust. And in 1999, we showed that they can have extremely high surface areas. They broke all records of surface area for 1,000 years. So the other thing that we've done, we use the same kind of thing to link organic molecules together to make what we call covalent organic frameworks or COFs. Back in 2005, we showed that you can make 2D COFs and 3D COFs, thereby extending organic chemistry into the infinite 2D and 3D regime for the very first time. These are new materials based on well-defined building blocks and made from covalent bonds linking organic molecules together. This material is only made from carbon, oxygen, and boron, some of the lightest elements in the periodic table. And it's crystalline, and it has a surface area, a very high surface area. We have also been involved in making molecular weaving, which I will not discuss today in the context of climate. So the strong bond and the building block approach is what's making this new chemistry so popular, being practiced in almost 100 countries around the world. Okay, so what do they look like? So here is they look like baby powder perhaps, or granulated sugar. And if you zoom in on one granule, you'll find that it's riddled with holes, okay? This is one granule. This is a crystal structure, an X-ray diffraction crystal structure of MOF5. And you see that the idea was, in those days, still is, can we take gases that fill very large space and compact them inside the pores? Why? Because the material is like a magnet to those gases, and therefore I can compact them next to each other better than they would be without the material. Almost like bees assembling on a honeycomb, okay? So gases like to repel each other, and when you put this material in a vessel, gases can be compacted within the pores. And so this is what they look like on the atomic level. If your eye can see the atomic assemblage of these crystals, you'll see things like this. The metal oxide is in pink or red, and then the organic is in gray. But everything you're looking at, whether it's the linker, the organic linker, or the junction, the metal oxide junction, are adsorptive sites. We found that the faces, edges of the 6-membered rings of the organic, as well as all the atoms in the metal oxide unit, are adsorptive sites. You can call them parking spots for gases to sit and next to each other in the structure. That's why this material has an extremely high surface area, 6,400 meters square per gram for each gram. A gram of this material is no larger than a, let's say, coin, okay, a quarter or so. But it has an internal surface area, an internal area, internal footage that would cover an entire football field. That's why in a vessel filled with this solid, I can store much more hydrogen or methane or CO2 than a vessel that doesn't have the solid. Okay, but the solid acts as a magnet to compact gases without having to use high pressure. And we have been working with BASF over the years and showed that, in fact, these materials could be scaled up to ton quantities. BASF is already scaling some of them in hundreds of tons for carbon dioxide capture applications. So the chemistry of these materials is not only can you make them with atomic precision, but you can also modify them with atomic precision. We didn't just make one material, but we made many materials by varying the length of the linker and the size of the metal oxide unit, the composition of the metal oxide unit, the composition of the linker, the connectivity of the linker. Everything you're looking at can be varied. That's the power of being able to control matter on the atomic and molecular level. So all these things can be varied, and in so doing, you're designing the functionality of the pore. You're designing what that pore is going to do, okay? So you're making really tailor-made materials for very specific application. Sounds like magic? It's not, it's real, okay? It's a dream come true for chemists. So we have opened an infinite frontier we call reticular chemistry, and it has infinite number of structures. Hundreds of applications are being pursued in the community. So, okay, let's talk about addressing societal problems. The problem of carbon capture can be divided into two parts. The first part is how do you take CO2 out of the air? Where it's dilute? Okay, there's lots of it, but it's dilute because it has other components in the air that you have to separate it from. 0.04% by volume, okay? And from point sources, meaning power plants or industries that burn fossil fuels, if you're burning natural gas, you're emitting 5% CO2 by volume of that, the gases that come out. Or if you are burning petroleum or coal, you're emitting 16% CO2 by volume. So materials that work here to capture CO2 from air will most definitely work here, and even better. Okay, so we don't need to make different materials. So if I can address this challenge, then I would have addressed this challenge. Okay, and so that's what we set out to do. So what are the minimum requirements for a carbon capture material? One, you need high capacity. Well, the high surface area that I showed you means that I can compact more in the pore, so I can get high capacity. High selectivity. You need to be able to pluck CO2 out of the air and only CO2, right? You don't want nitrogen or other components of air in there so that your material works efficiently. That I think we can do, and I'll show you. The material needs to be water stable. Okay, if the backbone is made from covalent bonds like carbon-carbon bonds and carbon-nitrogen double bonds, it will be stable. Okay, I'll show you shortly. Oxidatively stable, because there's oxygen. It needs to be cyclable. It needs to do hundreds of thousands of cycles without having to be replenished or replaced. And your regeneration temperature, once you capture the CO2, you want to be able to take it out, concentrate it, and for now, pump it under the ground until we find a way of converting it to something useful. So that's regeneration temperature. We want it to be as low as possible, okay? Not 120 degrees as is being done now, but much less than 120 degrees. And whatever you do, it needs to be scalable because it's a big problem. It's going to require hundreds of thousands of tons of this material. Okay, so we have a lot of materials that we're examining as a community. Carbon capture, aqueous amines, carbon zeolites. I won't go through each one of them, but all I want to say is that they don't work. They don't. That's why everybody that's not a scientist is doubtful about carbon capture. So this carbon capture problem is a big problem. And society hasn't quite decided what to do because there aren't materials that we can say they work, we have the solution, And here it is, and you need to make a decision as a society or as a government on capturing carbon dioxide. I think MOFs and COFs are at the forefront, and I'll show you some evidence of that. So here's the first MOF. This is a MOF made using procedures that we have outlined, but made by my colleague George Shimizu at the University of Calgary. It's called CAF 20. Okay, Calgary Framework number 20. Okay, it's made from zinc and oxalate and perazolate, very simple building units. And already it's being scaled up and used to capture CO2 from air. And this is what you need to consider. The capacity is 2 to 4 millimole of CO2 per gram. The industry wants at least 1 millimole. So this even does better than that. And it's been cycling since up to 2021, when this paper was published, more than 450,000 cycles, and it's still cycling. Okay, so, and it takes up CO2 from cement plants, where the CO2 concentration is varies between 14 to 35% by volume. This material will not work for capturing CO2 from air, but it's working for capturing CO2 from cement plants, where 1/3 of industrial production of CO2, emission of CO2, is from cement plants. So this is addressing a real problem. This material is already in plants, and it's already capturing CO2 and preventing CO2 from going into the air. There are 3 plants in Canada that are already using this material, as well as an experimental or a pilot in California, capturing CO2 from cement plant. BASF is using the work that we've been collaborating with to scale up this MOF to 100-ton quantities for those plants. So here is an innovation based on MOFs that's already deployed, and it's already capturing the CO2 and preventing CO2 from reaching the air. Okay, what about taking CO2 out of the air? Because as I mentioned, we still need to do that. The experiment to try is to take air, pass it through the material, and see whether CO2 is retained by the material. If it's retained, then you have a great material. If it's not retained, then you have a problem. So that's the experiment that we do. It's called kinetic separation. Well, this is a compound that we've been working on since 2005, when we first invented COFs. And in 2019, this student made a breakthrough. He can crystallize this kind of COF that is made entirely from carbon-carbon double bonds, carbon-carbon bonds, and carbon-nitrogen double bonds, the strongest bonds in chemistry. Nothing breaks this material down. Concentrated acids, bases, concentrated bases, even corrosive media like N-butyllithium and methyl lithium. This is a very durable material. Okay, so that's wonderful. And we use reticular chemistry to modify the interior of this material without touching the backbone, but attaching things to that backbone that will ultimately take CO2 out of the air. And here it is. So this is a modification of the material I just showed you. I'm not going to go through the chemistry, but only to say that we can install small polymers that are repleted with amines. Those amines, the amine sites are the sites that are going to go after the CO2 from the air, because amine is basic and CO2, they are selective to CO2. Without those amines, you cannot trap CO2 from air. And if you do, then you can't get rid of the CO2. But this is the right molecule that allows you to attach the CO2 to the amine and still detach it in an energy efficient manner. So this is the experiment. This is the result. We made the material. Zihui is showing it here in Berkeley, Campanile. But you can see here, it's a yellow, nice yellow solid. Okay, so he made a column of this, and he brought, using a pipe, air from outside, Berkeley air, and pass it through the material. Okay, of course, he did all the laboratory experiments and tried to understand how the material behaves and everything. I'm cutting all that out for time limitation, but I said to him, you're not going to solve society's problems unless you show that, in fact, it works under real conditions. So he did. He passed air from Berkeley into the material. And this is what he measured. This is CO2 concentration in the air. You see that Berkeley, because we're an industrial area, we're in a metropolitan area, CO2 concentration is much higher than everywhere else. It's almost 500 ppm. This is the humidity in the air. It varies between 20 to about 50% relative humidity. And this is the CO2 uptake. He ran this 100 cycles. Okay, take the CO2 in, take it out, and take new CO2 in from the air, take it out, and things like this. And you see immediately that, in fact, water in the air helps in capturing CO2. The higher the humidity, the better your CO2 uptake. But at all humidities, you're taking CO2 out of the air because water shifts the equilibrium towards carbamic acid and bicarbonate, both favored for CO2 capture because they only use one amine per CO2. And so so I looked at him when I saw this and I said, I think you solved the world's most challenging problem. It was very exciting. So if you just pick one humidity like 37, you can see that this material consistently and just the cycles, you can see that it's consistently taking up CO2 from the air without any degradation. That's the kind of durability that is needed for this to become commercialized. What's the uptake? At 50% relative humidity, the uptake is 2 millimole of CO2 per gram. That's for air capture. For methane, flue gas, it's also about the same, as well as coal flue. Okay, so this material works under all conditions of CO2 emission, whether they are from the air or from power plants. So what does this look like at scale? Okay, I already mentioned there are around roughly, okay, 1,100 gigatons of extra CO2 in the air that we need to capture. Now, this is our parameters for our material, 2 millimole of CO2 per gram and 10 minutes per cycle. Okay, so every 10 minutes, you can do one cycle of uptake and release. Now, let's say I have a plant that I have equipped with 100,000 tons of this COF. I can capture per year 0.5 gigaton in that plant. But let's imagine that in every city of 1 million or more, I place one of these plants. Do you know how long it takes to capture all the CO2 in the air, all the extra CO2 in the air? 3.5 years, less than 3.5 years. Can we do this? Has humanity done anything on this magnitude? Of course, chemical companies do this every day. Okay, if you don't want to put this plant in every city that is 1 million or more, let's do 200 cities of population of 2 million or greater, just in the China, US, and Europe. Okay? That's 11 years. So anyone that says it's not doable, it's difficult, it's energy intensive, they don't know what they're talking about. The cycling of this material only requires 50 degrees Celsius, okay? Much lower than what you would use with those liquid amines. So society already knows how to produce 200 million tons of chemicals every year. Just one chemical, sulfuric acid, 200 million tons every year. So this is possible. This is possible. And now we have the material progress, the technology progress, and evidence that, in fact, we have a material that works. And 100 cycles, no loss in performance, and therefore we can grade it to many, many years in a plant working in terms of carbon dioxide capture. So there is a solution. Okay, now that's CO2 capture. It remains for society to say that's a crisis, not a problem. It's a crisis, and we need to treat it as a crisis. When the pandemic was a crisis, when the housing collapse was a problem, we did something about it, right? Because it was a crisis. This, we need to look at it as a crisis to make sure that we shift our way of thinking. But we continue to emit every year about 40 to 50 gigatons. Okay, that's just added into the way that's just going to take us longer to take that CO2 out. But we don't have much time left, right? It's already the temperatures is reaching plus 1.5 Celsius because of CO2 emission. That's already, we're already there. And by the end of the century, the projections are about 3 or more, plus 3 or more degrees Celsius. And so CO2 from the air needs to be taken. We have a material that can do that. And we have a material that can do that very well. So now onto the water problem. There's a lot of water in the air. We want to use the air as a source of water, as a new source of water. Okay, there's almost 1,300 cubic kilometers of water in the air at any one time. That's as much, that's more than the rivers on our planet. Okay, if I give each person on our planet 50 liters a day of water, every single person, I would have only used less than 0.01% of the water that's in the air. So there is no chance of drying the air. And when we drink the water, it goes right back up there, right? It does not, we do not. Water doesn't get decomposed, okay? So there's plenty of water, and we want to use this as a resource so that we can create water independence in the world for every person. Every person should have a device that generates water. Okay, I'm going to show you how potentially we can do that. So the challenge of harvesting water from air is illustrated here. This is a psychrometric chart where you're plotting the water vapor in the air in grams per cubic meter versus temperature, and you get these relative humidity lines. Okay, 10%, 20%, so on. This is a dry region. This is the more water region colored in green. Okay, but let's imagine that I am in a city, in a Mediterranean city like Granada in the summer, where you are at 30 degrees Celsius and a humidity of 20%. If I was to take water out of that air, I need to cool down the air to 4 degrees Celsius. Okay, that's refrigeration. That's not economically viable. Now let's imagine that these materials that I've been talking about, I can program one of them to pluck water out of the air, concentrate it into the pores, and I can take that material and put it in a ball like this and cover it and expose it to the sun. What happens? The water will come out of the pores and condense on the walls of the ball. Now I have made drinking water. And that's exactly what a MOF does. A MOF takes arid air and makes it tropical air. Tropical air requires very little temperature change to condense the water. That's exactly how the MOF works. And that's how we got started here. We made an aluminum MOF. This is an aluminum oxide chain linked. These chains are linked by pyrazolate. And the material you can see here takes up water from 5% relative humidity, and most of the water at 10% relative humidity. This works in the Mojave Desert, in Death Valley, in the driest deserts in the world. And if it takes water at these low humidity, it takes water at all humidities. And so what I want to point out here is that this material has, if you're a molecule of water floating in the pores of this material, you will see almost like a grid that has hydrophilic regions and hydrophobic regions, hydrophilic, hydrophobic, along the entire pore. And so this beautiful attraction to CO2, to water in the hydrophilic region and repulsion through the hydrophobic region allows this push and pull to dictate how tightly your water is bound in there. You want it to be bound, but you don't want it to be bound too tightly so that you don't have to put in a lot of energy to take it out. Okay, so So we have done all of what you see here is a result of X-ray diffraction, not just on the framework, but also on the water that is going in there. So we have located where each water molecule is going. And you'll see the very first water molecule goes into the hydrophilic region, and it acts as a seed onto which other water molecules build through hydrogen bonding. We never take the first water molecule out. It stays there. It's very strongly bound. It acts as a seed. But the other water molecules that come after that can be taken out in an energy efficient manner. So here's one pore, and I'm going to slice it and show you the very first water molecule are going to be residing in the hydrophilic regions. Okay, another one there. And now they'll bridge over the hydrophobic region, okay, to fill the pores with water. And that's the way the MOF works. And the reason we know it works this way is because we have worked for a long time on crystallizing MOFs, making sure that we can characterize them on the atomic molecular level. So my students went to illustrate what I have been telling you. They said, Professor, we have to go to Death Valley to show that the MOF works there. Okay, and so they wanted a holiday, but they designed a device that you can put in a briefcase. And the device basically is made of pancakes of MOF. At night, you expose the pancake, you open the device, expose it to air. Water from the air goes into the MOF, and during the day, you close the device, and as it heats up, water comes out. Okay? No energy input aside from ambient sunlight. This thing is not plugged in. Okay, that's because the MOF is designed to take water from very low humidity. And this is the power of chemistry. And okay, so where do we go from here? Okay, they love this. Nature Water loved this picture of the device on this Downties view, which is overlooking the lowest point in North America.
All right, ready, 2, 3, action.
This is supposed to be to have voice, but that's okay.
Cheers.
Okay, Eugene drank the water because the water is ultra pure. This is the purest water you'll ever make. Okay, we tested it for metals, organics, any kind of contamination, any leaching, nothing. Any leaching from the material, there's nothing. This is distilled water. It doesn't really taste as well as Eugene is indicating to you because it's distilled, but to make it tasty, you mineralize it as we normally do with water. Okay, so if you want this to be in every household, we made an electrified device. And in this device is no larger than a microwave oven. And here this works in exactly the same way, except we use electricity to run the electronics as well as to heat up the MOF, okay, through direct heating. But it works in exactly the same way, but we can do more than one cycle a day. Okay, we can do 200 cycles a day. And now you can deliver 5 liters of water per day using only 200 grams of MOF. Okay, that's not even a handful. Okay, so 200 grams of MOF gives you 5 liters a day, every day, for 7 years. The material has been running for 3.5 years already with no degradation. Okay, so now we are at 22 liters per day. We have a device with 2 kilograms of MOF, okay? Now chemistry comes in. Okay, this is our MOF. This is our favorite MOF. It works extremely well. But if I can increase the uptake of this MOF without changing the particulars of where the water is going, I could get more people to drink water. So we added just 2 carbon atoms here. We can get 50% more water. Exactly the same structure, has all the great things that you want in the material in MOF 303, But now we have this, what we call long arm extension of two carbons, La2. Okay, that means that if I have a device like the one that you saw in Death Valley, made from a ton amount of MOF, now 50% or 50% more of my village can drink water. Okay, so these are just the technical particulars of that MOF. Now we have a program with GE, and we can now deliver 120 liters per day with less than 2 kilos. Remember, in the previous one, 22 liters with 2 kilos, now 120 liters per day. So we are increasing the efficiency of the. So how does this look at scale? For the independent water harvester that doesn't use electricity, that is entirely made from or makes water from ambient sunlight, 1 ton of MOF with no energy input gives you 3,000 liters of water every day for years at 1 cent per liter, just to start, okay? The active water harvester, the one that is plugged in, 1 ton of MOF gives you 60,000 liters of water per day at less than 2 cents a day. Okay, this is real. Okay, this is not Dune or Star Wars. This is real. This works. This is already demonstrated in the desert. This is already running, and this is already being commercialized. So we've been doing this. We've been going from a molecule to the material, engineering the material, integrating it into a device, and prototyping, right? And this took 30 years, okay, most of my life. Okay, and I'm delighted. But we can't afford to wait that long. So we're developing what I call the AI discovery cycle, where now you enable this cycle with robotics and AI, okay, so that we can make discoveries faster. Okay, we can make that next greatest water harvesting material, CO2 capture material, or other materials much faster. And we also want to enable this cycle, right? This is the scaling cycle. The cycle not just scale up, but enabling this cycle with AI means that everyone around the world can plug in, just like everyone can Google things. They should be able to design their own water harvesters if these things are enabled with AI. So we raised enough money to start what I call the AI for Science Institute, or BIDMAP, Baker Institute of Digital Materials for the Planet. And there, that's exactly what we're doing. We're trying to accelerate discovery and deployment of these materials. So here's what I'm not going to describe it, but the AI cycle already, and I won't talk too much more than this slide and the next slide, but 50% more discoveries are being done in a very short period of time, less than a year, okay, using this cycle. Even my students are using LLMs, 7 LLMs in this case, to create a research group where just through conversational language, you can cut down the discovery time from 3 years for COFs, for example. We wanted to make this COF for water harvesting. Okay, this is an all-organic COF. But crystallizing this or figuring out the conditions under which crystallize it will take 3 years. But it only took 2 weeks, from 3 years to 2 weeks using this LLM. And that's the power of what I'm talking about. Here's where we started no crystalline, and by experiment 84, using the LLMs, we have a crystalline material. Okay, so this is foundationally changing the way chemistry is being done. Now I have turned, in the last 2 years, I've turned my entire group into an AI group. You can do chemistry in my lab, but it has to be woven with AI. That's my requirement with my students. Here they are, and look how happy they are. Okay. I want to thank the financial support of these funding agencies, and thank you very much. It's a great honor to receive this distinct lectureship and this award. Thank you. I'm happy to answer any questions.
That was remarkable. There are undoubtedly questions. My colleagues will be circulating with microphones. If you just raise your hand, happy to take some questions. I think we have our first right here.
Thank you for an inspiring talk. I have two questions, or two areas of question. The first is sort of the engineer in me. How long does it take to actually build a plant to pull carbon out of the air? And are there any governments who are actually moving forward with that? And my second question is that the third leg of our climate crisis is the heating up of the oceans. And I'm wondering if by pulling carbon dioxide out of the air and water out of the air, if that does anything to the carbon dioxide that's saturated in the ocean.
So good questions. Plants that are already pulling CO2 out of the air, some of them with inferior materials, are already in place in Europe and the US. They are piloting very large plants. Some even commercialized plants for CO2 out of the air are already being built in Iceland. So the infrastructure, the plants exist. Of course, we have to build more of them, but that road has already been opened and we already know how to build them. So that's exciting. I already mentioned that plants that are capturing CO2 from cement plants are already built and they're already operating. So I think tremendous amount of capital is needed to build more plants to scale up the MOF to take CO2 out of the air. Now, concerning the other question about I'm sorry, what was it? The ocean. Oh, yes, the ocean. Well, a lot of the CO2 that goes into the air is also going into the ocean. I think that, of course, will be minimized, but still the CO2 that is in the ocean that's causing acidification has to be taken out. And there aren't very good ways of doing that right now. There are proposals for doing it electrochemically without spewing chemicals into the ocean, just using ions, chloride and sodium in the ocean to make carbonate, but you still need to capture that CO2 out of that cycle. So I think that that's less developed, but you're right. I mean, that's another aspect that is being worked on right now. It's not as advanced as CO2 from air. Yeah. Yeah.
Questions?
Two questions. First, when you're a long arm agent, you increased efficiency, but you put in an acrylic acid unit. So have you caused a decrease in stability? The first compound had gone for 3.5 years with no degradation, but that group will chemically not be potentially as stable. And the second, in the costs that you gave for operating the water capture system, was that the operational costs, or did that also include the amortized cost of making the COF that was being used for capturing the water?
So the first question, adding those 2 carbon atoms does not destabilize the MOF. Okay, we've had many ideas, and I'm happy to go through them, many ideas where the MOF was not stable, but this idea worked. And what it does, because they're hydrophobic, you don't take up water at 10% relative humidity, but most of the world doesn't live at 10% relative humidity, okay? That's Death Valley. So we're not worried about that, that it takes up water at 20% relative humidity or more. So that works very well and cycles very well. GE is very, very happy with it. Our startup is very, very happy with it. So it's a great material. The beautiful thing is that you can insert it like a surgeon without affecting anything else around in terms of where the water goes. Your second question about the cost has to do directly with the energy you're putting into the system. The rest is nothing. The rest is very inexpensive, okay, because the machinery is simple, off-shelf products. The MOF is going to be in the device for 7 years. So the capital investment, okay, it's something. I'm not saying it's nothing. But the operating expenses, that's all you have to worry about is the energy that you're putting into the system, the fans, the energy that the fan and the compressor. And it turns out that the fans and compressors are not very efficient. So you have to make sure you capture some of the energy that you're putting in and reuse it. So a lot of that low-grade heat, because you can take the water out at relatively low temperature, like 50 degrees or 60 degrees, you can use the low-grade heat or the waste heat to engineer systems that basically don't require any energy, any new energy, right? So if you put this device next to a power plant where there's a lot of low-grade heat being wasted, you don't need, that's why the cost is very little, yeah. So I wanna say that the engineers are absolutely brilliant. I've grown to love them, to respect them. They are the ones that bring this to fruition. You have to have the material, but beyond the material, the engineers have to come in. And that's what I have really been admiring through this project, yeah.
Can you talk a little bit about the challenges of storing the enormous amount of carbon that you'll be pulling out of the air? Does the technology exist to keep it underground? The costs of compressing it and energy costs and other costs of putting it underground? I'm not even sure what other aspects might be challenging, but could you address
Yeah.
that?
And the business of pumping it under the ground is well developed. Geologists will tell you there's plenty of space under the ground that is sealed where the CO2 is not going to come out for at least 100, and they even, some of them will say 200 years. And there are also some places under the ground where the CO2 will become mineralized. The cost of that plus the cost of capturing it is all amalgamated in what we always talk about as a dollars per ton of CO2. And right now, before this material, you're talking about 1,900, it was $1,000 per ton. This material, okay, in our startup, we think we can get down to 100, maybe even less than $100 a ton. Okay, again, because of that low-grade heat, because of the lower heat that you need to take the CO2 out. That's the beauty of the MOFs, is that we design them in such a way as to manage the binding energy of the CO2 or water, how strongly they bind to the framework. That's where your most energy cost is going to be, aside from the fans and the compressors, yeah.
Questions up front.
Hi, I have two questions too. Do you see any risk to human health due to prolonged exposure or ingestion of these materials? And you mentioned that it traps carbon, so how would you get that trapped carbon out of the materials themselves?
You just get it by heating the material up. There are different ways of doing it, but you can either heat up the material or pull the CO2 under vacuum, okay? And each one has its own scenario for energy efficiency, but both of them have been used and are viable. Your first question about ingesting it, I mean, it's a solid. You shouldn't be ingesting it. It's a, you know, you deal with polymers, it's safer than the polymers. In fact, the constituents of these COFs is not very different than polymers that make up the bottle of Coke. My concern is not about you ingesting it, it's about what CO2 is doing to you and to your home and to your livelihood. That's the serious problem that people are not aware. Our lives are being threatened by climate change, and a lot of people's livelihood, especially in developing world, is being affected by this. Yeah.
Let's take one more from this.
So my first question is, how many people would it take to like run one of these plants in terms of like creating job opportunity?
Very insightful question. I think once our society decides, you know what, CO2 capture is a problem, is a crisis, now you start thinking in a different way. And now new economies emerge based on all of what I have been discussing, because society now becomes thinking more about how do we do sustainable industry? How do we stop pumping, using natural resources of our planet to grow our companies? That's what's happening now, right? You extract, the more you extract, the faster you can grow. So growth, our economic growth, we need to start thinking about it in terms of sustainability, right? How do we use these new technologies to grow rather than start pulling more and more out of the ground? That's why I don't like electrical vehicles, because they're causing more problems, because you're extracting metals out of the ground, you're destroying the communities where the metals are, and it's just doing the same old thing without solving the real fundamental problem facing society. We should have invested in hydrogen instead of electrical cars. We should have invested in natural gas. We could have cut the emission by 50% already. We had a methane natural gas car that BASF had tested all over the world, and it was ready to be unleashed.
My other
But
question
It's
is,
not as sexy as electrical cars.
yeah. But probably also not as heavy. So,
It
because
wouldn't be
the
heavy,
electrical cars, the batteries
right?
put a lot of weight
Yeah.
on the bridges.
And you can resell. I mean, what is the resale value of your electrical car?
My other question is, how long does it like take to synthesize, say, like a gallon of water? Like what's the
Oh, well,
time for that?
it depends. That device that I showed, the electrified device, that gives you 5 liters a day. So that tells you how fast, but how fast depends on how much MOF you have, depends on how high you heat, all kinds of things like that. But you're not going to be waiting for the water to come out, because it will be pumping from the air day and night, and there'll be a reservoir.
Thank you.
Yeah. Yep.
Let's give the good doctor one more round. Thank you for an extraordinary presentation. But there's more. So it is our tradition here at the Science History Institute to honor our Ullyot lecturers with the presentation of the Philadelphia Liberty Bowl in recognition of their extraordinary accomplishments in service to science and humanity. And it is now my pleasure to invite to the stage Dr. Kay Lee, Chair-elect of the Delaware section of the American Chemical Society, to present the Liberty Bowl to Dr. Yaghi. Sir.
The Delaware local section of the American Chemical Society present you the Liberty Bowl.
Thank you. Thank you.
Do one more here. Precious cargo.